We are really excited to present in the AppSec Village. And today we are going to talk about BOLABuster, our methodology that we developed in order to automate BOLA detection at scale using LLMs. But first, let's introduce ourselves. So my name is Ravid. I'm a security researcher at Palo Alto Networks. I expertise in the OWASP field, which is web application and API security mainly. And in my free time, I enjoy watching football games, traveling the world, and take care of my dog, Mabel.
Hi, my name is Jay. I am a security researcher with Palo Alto Networks, and my research has been focusing on identifying the threat and risk in cloud environment. And recently, I've shifted my research focus towards generative AI, in particular looking into the potentially adversarial use of generative AI. When I'm not working, I spend most of the time with my hyperactive twin boys. They behave just like minions and head off to the parent there with young kids. I know how difficult it is to take care of young kids when working. And I'm also a cat lover, so I also spend a lot of time scrolling to funny cat video when I'm not working or working.
Great, so let's go over the agenda for today. So we are going to cover the concept of BOLA. We will show you our methodology of automating BOLA hunting using LLMs. You are going to see a real BOLA testing that is part of our methodology. And finally, you will see how we hunted down 17 new BOLA vulnerabilities in one of the most popular open source projects out there. And yeah. So broken object level authorization, or short for BOLA. Our motivation for the research was pretty huge, I would say. For those of you who are not familiar with BOLA, it is ranked at the top risk at the OWASP API top 10. And it is also the fourth most reported vulnerability in HackerOne. So it's really popular and it's really severe. And yet, there is no automation tool that can actually and reliably detect BOLA at scale. So all of this was a big reason for us to try to solve basically an unsolved issue today. And let's understand first what is exactly BOLA. So if you take a look at this example, we have a clinic application. And we have a patient that can query his visit ID and get his doctor notes. Pretty straightforward. But what would happen if this patient would decide to act maliciously and try to fetch another visit ID that does not belong to him? If he would be able to do it, it means that the backend will have an authorization issue. And this is basically a BOLA. So in a straightforward way, if I can delete or modify, let's say, Jay's comment from Twitter or Instagram, this is a clear BOLA because I shouldn't have the permission to access, modify, or delete another user object that does not belong to me. And the consequences can be huge. It can start from data leaks to data manipulation and even the full account takeover, as we will see today. We faced many challenges when we tried to automate the process of BOLA detection. The first was the complex authorization mechanism. So application these days actually has typically multiple users with multiple roles, with multiple resources. So it's very difficult to say which user can do what, which user is allowed to do which action exactly. And this really can get complex. Also, applications are stateful today. So each action you make or each API call you make can affect the state of the application. And basically each endpoint is dependent on one another. So imagine you try to delete a comment from an article or a post. So first you would need to create this post and create a comment for this post, and only then you will be able to delete this comment. So they are dependent on each other. You cannot isolate one of them. And the execution order is really important in order to not have any technical issue. So it is a big challenge to understand these endpoint dependencies, actually. Also, BOLA doesn't have there is a lack of vulnerability indicator, basically. So unlike XSS or SQL injection, which is pretty straightforward to recognize the pattern of the payload, BOLA is a logical error. So it's not really malicious by definition. So it's hard to analyze and understand whether it is a BOLA or not. And lastly, the context. So we try to understand which endpoint in the application and which parameter contains sensitive data. And it's not that easy to understand it. And also to understand what is the impact, actually, of each action that we can take in the application. So all of this was pretty big challenges that we faced during the process.
Thanks, Ravid, for covering the background. I hope everyone understands why automating data BOLA detection is difficult. So it was only 2 years ago that we realized that AI may be able to give this problem a glimpse of hopes. Because of the recent advancement of AI, we were provided with new tools to solve the problem that were not possible to solve in the past. So, and also in particular, our challenge of extracting context and logic information from textual data aligns well with the capabilities of large language model. So that's the start of our journey in using AI to solve BOLA detection. Here's a high-level overview of our methodology. The only required input of our methodology is an Open API spec or a Swagger spec. The first stage identifies the endpoint that can be vulnerable to BOLA. Not every endpoint can be vulnerable to BOLA. We used AI to help analyze every endpoint and its parameters to select a subset of endpoint as our target. This step helped us narrow down our target endpoint and avoid wasting time on the endpoint that are not at risk. We call this endpoint as potentially vulnerable endpoint, short for PVE or target endpoint. We will refer to this endpoint as target endpoint or PVE in the rest of the talk. The next stage uncovers the dependency relationship between endpoint. Modern web applications are complex, typically one endpoint depending on many others. For example, in order to test an endpoint that updates an invoice, you first need to call the endpoint that creates the invoice. And in order to create an invoice, you first need to call the endpoint that creates the transactions that can be included in the endpoint. As a result, it is crucial to understand the endpoint that my target endpoint depends on before I can accurately test it. With the endpoint dependency relationship identified, the next stage calculate the execution path to each target endpoint and create a test plan for each target endpoint. The next stage then transform the test plan into multiple executable bash scripts using large language model. There may be one or multiple execution paths to each target endpoint, and we aim to cover as many paths as possible. Finally, we set up a target API server and run all the test script generated in the previous step. The process of user registration, user login, and token refresh have all been automated. And we also use AI to help analyze the response and logs produced during the test. Let's dive into a little bit more detail in each stage. In the first stage, we try to identify the endpoint with input parameter that reference private, sensitive, or confidential information. These are the endpoint that we target. These are our target endpoint. For example, let's look at the first endpoint. The username here indicates that the endpoint may reference to data associated with the individual. If this endpoint is vulnerable to BOLA, an attacker may be able to reset another user's password. Similarly, if the second endpoint put user email is vulnerable to BOLA, an attacker may be able to change another user's email. Traditionally, pen testers manually look for this endpoint and their parameters to determine their target endpoint. This process is slow and cumbersome, especially for very large applications with hundreds of endpoints. So we use AI's capabilities of reasoning and understanding text to automate this step. Here is a snippet of our prompt that shows how we teach AI to recognize parameters that may reference to sensitive data. Essentially, we instruct AI a set of rules and examples. At the end, AI returns us the endpoint and parameters that meet any of the conditions that we provided. The next stage uncovers the dependency relationship between endpoint. As I mentioned, due to the complexity of modern web application, each API call may change the state of the application and affect the outcome of other API endpoints. As a result, it is crucial to identify their dependency relationship before we can test them. In this diagram, we call the endpoint on the right as consumers and the endpoint on the left as producers. Producer endpoint output the values that consumer endpoint need as input. Again, producer endpoint output the values that consumer endpoint use as input. This is one of the most important concepts in our research, in our methodology. Let's look at this endpoint as an example, delete user. In order to correctly test this endpoint, we need to feed it with an existing username. If we feed it with a random variable, a random username, this endpoint will always, the API call will always fail and give us meaningless result. That's why we need to identify its producers. In this case, this consumer endpoint has 4 producers, and each of them can output the existing username that the endpoint can use. Here is a snippet of the prompt that we use to teach AI how to recognize dependency relationship. I want to emphasize that also we can use heuristic algorithm to match the output parameter name of an endpoint with the input parameter name of a consumer. This heuristic algorithm is not reliable. The reason is that developers sometimes use different parameter names to reference the same data object within the system. Developers may also use the same parameter names to reference different data objects across the system. That's why we use a combination of heuristic and AI to uncover the dependency relationship. We need AI to analyze each endpoint functionality in order to establish their dependency relationship based on their functionalities. Once we have using the dependency relationship uncovered in the previous stage, this stage builds up a dependency tree for each potentially vulnerable endpoint. In this dependency tree, the root node represents one of our target endpoint, or PVE. And any 2 directly connected nodes in a tree represent a consumer and producer relationship, in which the parent node is the consumer and the child node is the producer. Let's use the upper half of a tree as an example. In this case, endpoint is a producer of PVE. Endpoint output the value that PVE needs as an input. And endpoint 1 itself also has two producers, endpoint 3 and 4, which produce the output that endpoint 1 needs as the input. Finally, in the next stage, we calculate the execution path to each potentially vulnerable endpoint. So in the dependency tree, a path from the leaf node to the root node represents an execution path. This is a reverse tree traversal. So the path is actually from the leaf node to the root node instead of from the root node to the leaf node. And let's plug in some real endpoint to see how we do the calculation. In this example, the target endpoint is delete comment. And this endpoint has two producers, get comment and post comment. And these two producers in turn also each has two producers. So at the end, there are 4 execution paths that can all reach the target endpoint, delete comment. In the last stage, we then turn each execution path into an executable bash script using large language model and run the script to actually send HTTP requests to the target endpoint. The process is more complicated than just generating and sending the request, as Ravid will explain in the next few slides.
Great. Thank you, Jay, for the overview of our methodology. And before we can see actually a real BOLA test and view our BOLA that we found, let's see the prerequisites that we have before we can create an actual test. So we use LLMs again to create the user registration process and to collect the login data of the application. So basically we LLM generates user credentials that meets the criteria in terms of the, for example, password complexity and etc. And we execute the user registration process and we fetch the login data from the spec. So this is crucial in order to then log in the users of the specific test and get a valid and unique token for each one of them. This information will be stored in a dedicated file, so we will have an easy access and usage. Then we will want to isolate the test data. So if you ever saw a Swagger or Open API spec file, you know that it can be huge. It can be 1,000 lines of code, especially for the bigger applications. And we want to isolate only the data that is needed for the specific test. So Jay mentioned that we have a consumer and producers in each test, so we would like to have only the data which is relevant to these endpoints. So we will create a new file, we will feed it to AI, and it will save us about 90 to 95% of the spec. So we do it for efficiency to ensure that LLM will get only the accurate data that it actually needs for each test creation. And for cost, we want to have as lowest tokens as we can. And finally, we're creating the test script. It will be saved as an executable bash script. You can see an example of a very simple consumer and producer. We have a put user password and a get user to get the username. This kind of test will be saved in a put get directory. Put would be the parent, get will be the child. And the test generation actually runs asynchronously in order to save time. And right now we averaged 1.5 seconds for each test creation. Right, so the final step would be to actually run the test script in the application. So we have an execution order, and our main goal is to avoid any chance that a test would fail due to technical reasons. So we want the test to fail only if the PVE is not vulnerable to BOLA, as should be. So we will first run the tests that populate data and resources to the application before we can fetch them. And also we will try to push and delete, to push update and delete operation to the end. So we won't experience a scenario where we delete a user or delete a resource and then try to fetch it. So again, the main reason for this is not to have technical issues in a test that will make it fail eventually. So right after we finished preparing our methodology, we wanted to evaluate our BOLABuster actually and see the result. So what we did is we took maybe the best API fuzzer, which is open source right now, which is Wrestler. Wrestler is a Microsoft developed API fuzzer. You can find it on GitHub. And its goal is to automate the process of API testing and to find vulnerabilities, like our goal. So what we did is we took 3 open source applications which are deliberately vulnerable to the OWASP API top 10. We took Vampy, Capital, and Crappy. You can see from the table that they have a known BOLAs. And we started to test our tool against Wrestler. As you can see, Wrestler could not identify any BOLA of these applications. And it made a pretty big number of API calls, thousands and even hundreds of thousands. Then we tested our tool, again the same application, and the results were amazing. I hope you can see, we found all the BOLAs in each one of the applications, and we made significantly lower API calls. So eventually we made less than 1% of the calls that Wrestler made. So this is a crucial part. It proved our efficiency, and we didn't make the application load too much. Finally, we wanted to have a 100% true positive rate. So our goal was to find any BOLA if it exists in the application. We did have some false positive. You can't avoid it. But again, our main goal was to focus on the true positive rate, which was 100%. Now we can take a look on a real scenario for a BOLA test. So we have this high-level example where first Alice creates an article, then Alice creates a comment for this article, and then Bob will try to delete Alice's comment, which is the PVE. So first, Alice and Bob will log into the system. They will get a unique token which will be saved. Alice will create a new article in the system. We will save the article title. We will do the same with the comment. So Alice will create a comment. We will save the comment ID. And finally, the PVE, the maliciously Bob, will try to attempt to delete Alice's comment. And this scenario can have 2 results. If it will be successful, we will have a potentially BOLA for this endpoint. Or if the application can defend the BOLA as well, so it will be forbidden. Let's see the actual snippet of our code. So first of all, we will create a unique random string each time. So we will be able to create an article for multiple tests without getting an error that it already exists. So as you can see, we make a post request to /API/articles. You can see that we use user A token, which reference to Alice, and we use the article title as a random string. We will save the slug, which is in this case the article title. Next, Alice will create a comment. So what's special about this is that if you take a look at the actual endpoint, you can see that we dynamically use slag. So we saved this parameter from the previous request, and then we dynamically use it. So now we can reference to it as we can know that this resource actually belongs to Alice. Again, we save the comment ID. And then finally, we have the PVE, the delete operation. You can see again that we use slag and comment ID that belongs to Alice. And the main difference, and now we use the user B token. So now we can identify that this request is made by Bob and not Alice. And lastly, we will check if the test passed. Now, I want to emphasize that actually every BOLA test that we make is, if you think about it, is malicious by definition. The last request, the PVE, we will try to perform an action that you shouldn't be able to perform, right? Bob shouldn't be able to delete Alice's comment. So in case it is successful, we can mark this test as at least potentially vulnerable to BOLA before we can make further analysis and verification, let's say, in the application context. So you just need to understand that every BOLA test is malicious by definition. So let's see how we actually hunted some BOLAs in the wild. We have a quick demo of showing the running of the tool. So this is a Python based. And it will, I hope you can see, it's testing each API endpoint, and in case the result is successful, it will mark it with BOLA found and the actual API endpoint. After this, we will take the list and we'll further analyze it and try to understand if this is a real BOLA or not. So all of these applications, it has something in common. We found BOLAs in it. So first of all, Harbor. It is a cloud-native container registry. It is basically equivalent to Docker Hub, which I'm sure most of you are familiar with. It is a CNCF graduated project, so it's been in the wild for a while. It has around 2 million downloads these days. And we actually found, this year we found a new BOLA, which we will talk in a bit. Next up, Grafana. It's a data visualization and monitoring tool. Very, very popular. It's being used by 20 million users actually these days. And we also found a new BOLA there. And lastly, we have Easy Appointments, which is an open source tool. It has almost 200,000 downloads, and we actually been able to find 15 new BOLA vulnerabilities there. Yeah, little bit. The most amazing thing about it is actually that 7 of them are critical. So they got a CVSS of 9.9, which actually allows a low privilege user to gain admin access. Remember we talked about compromise? So we have a full application compromise in this case. Let's talk about Harbor vulnerability. It's pretty interesting. So Harbor has projects in it. You can have roles, so you can be an admin, a maintainer, a developer, or a guest. Basically, we found the vulnerable feature to be the project configuration metadata. So I hope you can see the attributes there for the configuration. Basically, an admin can change the project to be private, public. You can implement some image vulnerability scanning and have more power. So Harbor claimed that in their official documentation that only the admin project should be able to create and modify this kind of configurations, which makes sense. And actually, we found out that an unauthorized user can do the same operation. So we tried to play with the roles of the project, and we saw that the maintainer, for example, could not make any change via the UI. So this is a maintainer login, which is grayed out. You cannot modify it. But maintainer can actually create, delete, and modify these attributes via the API. So there is a big discrepancy between the UI and the API behavior. And this vulnerability actually create an extend in the maintainer privileges. So now a maliciously maintainer could be able to make a private project public, deploy unverified images, and actually control every configuration that you can control in a project. And as you can imagine, the consequences can be pretty high. So we can compromise the wall integrity of a project and actually the security posture. So Harbo verified, that's it. Okay. So just would say that Harbo identified this vulnerability, and you can find it in their security advisory. We got a CVE, and you can check out our blog about it when we technically talk about how we found this BOLA.
Thanks. I will just use the last 30 seconds to share the most important lessons we learned from working with AI. First, AI isn't always the best solution. Problem with existing heuristic solutions should not be solved by AI, like sorting, finding trees, or solving equation. Those problems have existing optimal solution, and always use heuristic rather than AI. Second, don't trust, always validate. Blindly trusting the output of AI can be very, very dangerous. So always validate the output of the AI before using them or passing them to the next stage. Finally, makes AI's jobs easier. Treat AI like a very capable junior worker who can do simple tasks exceptionally well, but can start making mistakes when the job becomes more complex. So when working with AI, it is always a good idea, good strategy to use divide and conquer to simplify its task. And thank you so much.